In a deep image of the sky, a galaxy merger can look like a single frozen shape. Two bright centers, curved streams of stars, knots of blue light, and long arcs, pulled far beyond the bodies that made them. The picture is still, the physics is not. A merger can unfold for hundreds of millions of years. Gravity changes the paths of entire stellar populations, draws material into tails, and rearranges the structure of both galaxies. Yet even while the galaxies pass through one another, direct collisions between individual stars are expected to be rare. Stars occupy so little of the volume inside a galaxy that most of them simply follow new gravitational paths through a system whose overall shape is being rewritten. The gas does not behave the same way. Gas fills the space between stars as a continuous medium. When large reservoirs from two galaxies are forced into new orbits, they can meet, compress, lose angular momentum, and move toward denser regions. That difference between stars and gas becomes one of the central clues. In some mergers, that disturbance creates exactly what astronomers have learned to expect. Dense regions collapse, young clusters appear, dust warms around newly formed massive stars. A galaxy that was already making stars can briefly make them faster. And then comes the harder part of the story. Some merger remnants do not continue in that direction. After the galaxies finally coalesce, star formation can fall rapidly. Large observational samples now show a pronounced excess of recently quenched systems during the first several hundred million years after coalescence. Yet simulations also show that rapid quenching is far from automatic. Many merger remnants retain substantial reservoirs of gas and continue forming stars. So the question is not whether mergers can create stars. They can. The question is how the same encounter can first arrange the conditions for stellar birth, and later leave a galaxy unable to use the fuel that remains. That shift does not require one universal mechanism. In one system, part of the available gas may be consumed during an intense burst. In another, an active central black hole may inject energy and momentum into the surrounding medium. Elsewhere, molecular gas may remain present while turbulent motion makes collapse less efficient. Observations of recently merged galaxies have even found substantial gas reservoirs where simple exhaustion alone cannot explain the decline in star formation. The remnant itself can change as well. Ordered stellar disks can be disrupted into rounder structures. Gas can be moved inward, outward, or into disturbed orbits. Beyond the visible galaxy, material in the surrounding halo can be heated or redistributed, changing the future supply of fuel that might otherwise cool and return. None of these processes acts alone in every merger. That is what makes this story more interesting than a simple before and after picture. A merger is not a switch that turns star formation on, followed by another switch that turns it off. It is a long redistribution of gravity, gas, angular momentum, heat, turbulence, and fuel. Different parts of that redistribution can favor collapse at one moment and resist it at another. The result can be a galaxy filled with aging stars, carrying the structural traces of a major encounter, with enough gas still present to make the absence of new stars difficult to explain. To understand how that happens, we have to follow the merger from the beginning, not as a single moment of impact, but as a gradual change in what gravity allows matter to do. And the first thing gravity changes is the shape of the encounter itself. The first close passage begins long before either galaxy looks like a single object. From far away, the gravitational field of one galaxy begins to reach across the other. The pull is not equal everywhere. The side facing the companion feels a slightly stronger attraction than the side turned away, and that difference matters more than the overall force. Across tens of thousands of light years, a small imbalance can reshape an entire stellar disk. This is the same basic idea behind tides on Earth, only carried into a system so large that the response is written in stars. Material on the near side is pulled a little harder. Material on the far side lags behind. Over time, those differences stretch the galaxy into long arcs. Spiral arms become distorted. Outer stars are drawn into tails that can extend far beyond the main body. Bridges of stars and gas may form between the two galaxies, tracing the gravitational connection that has developed between them. None of this requires stars to strike one another. A star behaves almost like a single moving point inside the larger gravitational field. Its path can bend sharply on a galactic scale, but the space around it remains mostly empty. Even while two galaxies overlap, their stellar populations can pass through one another, with direct stellar collisions remaining rare. What changes is the map of gravity each star is moving through. Orbits that were stable for billions of years can become elongated, tilted, or displaced. Gas cannot pass through the encounter so cleanly. Inside a spiral galaxy, much of the material needed for new stars lies in a broad rotating disk. Atomic gas, molecular clouds, dust and denser regions all share in that rotation. Before the encounter, angular momentum helps keep this material moving around the galactic center rather than falling directly toward it. Then the companion galaxy disturbs the symmetry. The disk is no longer responding to a nearly balanced gravitational field. Bars can strengthen. Spiral patterns can become more pronounced. Large regions of gas begin to exchange angular momentum with the surrounding stars and with the rest of the disturbed system. Some material moves outward. Some loses enough angular momentum to begin migrating inward. The inward moving gas matters because density changes what gravity can do. A molecular cloud may already be cold and heavy, yet still remain supported against collapse by pressure, turbulence, magnetic fields, and its own internal motions. Compress that same cloud, however, and self-gravity can gain ground. Regions that were previously stable can become unstable. Smaller concentrations gather inside larger ones. Dense cores appear. Eventually, some of those cores cross into collapse, and new stars begin forming. The first passage can help create those conditions in more than one way. As the gaseous disks overlap, streams of material moving at different speeds and in different directions can meet. The result is shock compression. In astrophysics, a shock does not have to resemble an explosion. It can simply be a narrow region where the state of the gas changes rapidly because one flow encounters another. Density rises. Temperature may rise as well. Turbulence is stirred into the surrounding medium. That mixture of compression and turbulence is already a warning that the outcome will not be simple. Compression favors collapse in some places. Turbulence can either create dense pockets or make larger regions harder to collapse. Gas pushed into a narrow overlap zone may form stars efficiently, while gas drawn into a long tidal tail may become too diffuse. Material driven toward the center may accumulate for a later burst. Other material may be heated, scattered, or left in disturbed orbits that take hundreds of millions of years to settle. So even during the stage most easily imagined as the beginning of a starburst, the merger is dividing its fuel into different futures. Some clouds become nurseries, some become reservoirs, some are carried outward, some are stirred faster than gravity can gather them, and much of the gas remains undecided for a long time. That long interval is important because a galaxy merger does not finish at first passage. The two systems may sweep past one another, separate again, and travel outward until their shared gravity slows the motion. For a while, they can appear to be moving apart. The tidal tails remain stretched behind them. The disks are disturbed but still recognizable. Newly formed clusters begin aging even while the galactic centers are growing farther apart. Then the outward motion stops. Gravity has not released either galaxy. The pair is still bound, and the separation is only another stage of the orbit. They begin to fall, toward each other again. If you could watch from a distance large enough to contain both galaxies in one view, almost nothing about this would resemble the speed we associate with catastrophe. The tails would lengthen over millions of years. Bright knots would appear in scattered regions. The central bodies would move together, pass, recede, and return on timescales longer than entire species have existed on Earth. There would be no single instant when the merger could be pointed to and called finished. Every image would be one frame from a process whose previous frame might lie tens of millions of years away, and whose next meaningful change might require tens of millions more. From where you are now, even the light-carrying images of real merging galaxies has crossed millions of years before reaching us. What astronomers receive is not a live event, but a preserved stage in a sequence too long for any person to witness from beginning to end. That limitation has shaped how mergers are understood. Astronomers compare many systems at different stages. One pair is still approaching. Another has completed its first pass. Another shows two nuclei buried inside a disturbed envelope. Another has only one central body remaining, with faint tails revealing that two galaxies were once there. Together, these snapshots can be arranged into a physical story. And for many years, one part of that story seemed especially convincing. If gravity could drive gas inward, if shocks could compress molecular clouds, and if dense gas was the raw material from which stars formed, then a major merger between gas-rich galaxies seemed to offer a natural route to intense star formation. Simulations and observations do show that interactions can enhance star formation, although the strength and location of that response vary widely from one encounter to another. The physics behind that expectation was real. The mistake was assuming the response would always be the same. A large part of the old starburst picture was built from light that human eyes cannot see. Dust aid changes the appearance of a galaxy. Invisible wavelengths, dense dust can hide regions where young stars are forming. The same dust absorbs ultraviolet and visible radiation and releases much of that energy again in the infrared. A galaxy whose most active regions are concealed in ordinary photographs can therefore become conspicuous when observed at longer wavelengths. As infrared astronomy matured during the late 20th century, astronomers began finding galaxies whose infrared output was remarkably strong. Many belonged to the classes now called luminous infrared galaxies and ultraluminous infrared galaxies. And when these objects were examined more closely, a recurring feature appeared. A considerable number showed disturbed shapes, double nuclei, tidal extensions, or other signatures associated with interactions and mergers. The connection was difficult to ignore. Here were galaxies releasing enormous amounts of energy through dust, often while displaying the visible scars of gravitational encounters. Young massive stars could heat that dust intensely. Active galactic nuclei could contribute as well. In many systems, both processes were present. The merger seemed to provide a natural explanation for why so much activity had been concentrated into such a small region of space. The theoretical picture forming around these observations was appealing because each step followed from familiar physics. A rotating gas disk carries angular momentum. That angular momentum is one of the reasons its material remains in orbit rather than falling directly toward the center. During a major interaction, however, the gravitational potential of the galaxy becomes asymmetric. Bars, spiral distortions, and other large structures can arise or strengthen. These structures exert gravitational torques on the gas, changing its angular momentum and allowing part of it to migrate inward. Numerical work has repeatedly shown that merger-driven torques can produce strong gas inflows, especially during the later stages of major encounters. The farther inward the gas travels, the smaller the region into which a substantial amount of material is being packed. Density rises. Molecular clouds encounter one another more often. The interstellar medium becomes increasingly compressed and disturbed. Regions that were already close to gravitational instability can cross into collapse. New stars begin forming from material that, before the encounter, might have remained in comparatively stable orbits for much longer. The idea did not require anything exotic. Gravity disturbed the disks. The disturbance removed angular momentum from part of the gas. The gas moved inward. Higher densities favored the formation of stars. Early merger simulations captured this sequence well enough that it began to feel like a general rule. In calculations of comparable mass disk galaxies, strong inflows could develop and star formation could rise dramatically, particularly near final coalescence. Some simulated remnants also resembled the luminous infrared merger systems that astronomers were observing. For a time, the pieces seemed to reinforce one another from every direction. Observations showed disturbed infrared bright galaxies. Dynamics provided a mechanism for moving gas. Simulations produced bursts after encounters, and the stars themselves supplied the energy that heated the dust, making the process visible in infrared light. There was no obvious reason to discard any part of the picture. Much of it remains correct. Galaxy mergers really can generate strong inflows. They really can produce dense gas. They really can increase star formation, sometimes by very large factors. Modern simulations that resolve the interstellar medium in much greater detail still find powerful merger-driven starbursts under favorable conditions. They also show that the process is more complicated than simply moving all available gas into the nucleus. Dense cloud formation, fragmentation, local compression, and stellar feedback can determine how much of the gas actually reaches stars. The change in understanding came from learning how many different things could happen between the beginning of an inflow and the birth of a star. Gas reaching a denser environment has not completed the journey. It can collapse. It can also be heated. It can be accelerated by stellar winds. It can be disrupted by supernova explosions from stars that formed slightly earlier. It can become turbulent enough that some regions collapse while neighboring regions remain supported against gravity. It can be pushed outward again, and some of the material driven toward the galactic center can continue past the regions of star formation and become fuel for the central supermassive black hole. Feedback, therefore, enters the story almost as soon as the starburst begins. Massive young stars do not simply appear and remain passive. Their radiation interacts with surrounding gas. Their winds inject momentum. After short stellar lives, many end as supernovae, adding more energy and motion to the interstellar medium. High-resolution simulations show that this feedback can disperse giant molecular clouds after only part of their mass has been converted into stars, regulating how efficiently a merger consumes its gas. So the gas inflow can be strong while the conversion of gas into stars remains limited. That distinction was harder to capture in older calculations. Resolution matters because a galaxy is not filled with one smooth fluid. Its interstellar medium contains cold molecular clouds, warmer atomic material, ionized regions, dense filaments, cavities opened by feedback, and turbulence across many scales. When simulations began resolving more of that structure, the starburst stopped looking like a single centralized response and began looking like a competition among processes operating simultaneously. The observations were becoming broader as well. The first luminous infrared systems had been scientifically valuable, but they were not a neutral sample of all mergers. Selecting galaxies because they shine brightly in the infrared naturally favors systems where dust is already being heated strongly. A merger with little cold gas weak star formation, or a modest infrared output is much less likely to stand out in a survey built around infrared luminosity. In other words, some of the encounters that first defined the merger-starburst connection were the encounters most capable of displaying that connection. The quieter cases were always part of the population. They were simply less conspicuous. Once larger samples could include interacting galaxies across a wider range of masses, gas contents, stages, and environments, the diversity became harder to treat as a secondary detail. Star formation is often enhanced during interactions, but the amount of enhancement varies. Different regions inside the same merging pair can respond differently, and modern resolved studies show that the distribution of gas and star formation during an encounter can depend on the properties of each galaxy rather than following one universal nuclear pattern. Mass ratio matters too. A small companion can strongly disturb itself while producing a much weaker response in a massive primary galaxy. Simulations have found that the efficiency of merger-induced sharp star formation generally falls as the merger becomes more unequal, while internal galaxy structure can either encourage or resist the instabilities that drive gas inward. Then there is geometry. The direction of the disks, the path of the encounter, and the distance of closest approach all influence how gravitational disturbances develop. But even here, there is no single geometric rule that determines the outcome by itself. Some simulations find only modest dependence on orientation compared with factors such as internal structure and available gas. A merger, then, is less like a machine with one output than a physical experiment whose initial conditions are never quite repeated. Two galaxies arrive with histories already written into them. One may carry a large reservoir of cold molecular gas. Another may have spent much of its fuel billions of years earlier. One may contain a disk that readily develops strong gravitational instabilities. Another may be stabilized by a substantial central bulge. One central black hole may remain faint through most of the encounter. Another may receive enough inflowing material to become a powerful active nucleus. The gravitational encounter acts on what is present. It does not supply what is missing. That becomes especially clear when two mergers with superficially similar shapes produce very different levels of star formation. The long tails may look alike. The nuclei may sit at similar separations. Both systems may carry the visual signature of a major disturbance. Yet, beneath those visible similarities, the gas can be following very different paths. And once astronomers began looking closely enough to see those differences, the old question changed. Instead of asking why a merger creates a starburst, it became necessary to ask what a merger must contain before a starburst is possible at all. There is no single moment when a merger becomes a starburst. The galaxies may already be close, their disks may already be distorted, gas may already be streaming inward, young clusters may already be appearing in scattered pockets, and still the system may never cross into the kind of sustained, intense star formation that gives a starburst its name. What matters is not one condition, but a sequence of conditions arriving together. The first is fuel. It's formed from cold, dense gas, and a merger cannot create large numbers of new stars if the galaxies entering the encounter have very little usable gas left. This sounds almost too simple to be worth stating, yet it explains a great deal of the diversity seen from one merger to another. Two spiral galaxies carrying rich molecular reservoirs enter the encounter with possibilities that two gas-poor galaxies do not. But, even here, the relationship is not as simple as more gas producing a larger merger-induced burst. A gas-rich galaxy may already be forming stars rapidly before the interaction begins. Its disk may already contain unstable clouds, dense filaments, and active star-forming regions. When a merger arrives, the absolute rate of star formation can become very high, while the increase relative to the galaxy's previous state remains modest. A more gas-poor disk may show a larger proportional change and still form fewer stars in total. So astronomers have to ask two different questions. How rapidly is the galaxy forming stars? And how much did the merger increase that rate beyond what the galaxy would have done on its own? Those are not always the same story. The second condition is the strength of the encounter itself. When two galaxies of comparable mass approach each other, each has enough gravity to reorganize the other substantially. Their disks can be stretched, warped, and driven into strong non-circular motions. Gas loses angular momentum. Large amounts can move inward. The disturbance reaches both systems deeply. When the mass ratio is much more unequal, the smaller galaxy may be heavily damaged, while the larger one experiences a milder response. It still feels the encounter. Its spiral structure may change. Gas may be displaced, but the global inflow can be weaker, and the resulting burst of star formation less pronounced. This is why astronomers separate major mergers from minor ones. The boundary is a convention rather than a law of nature, but the distinction reflects real dynamics. Comparable partners can rearrange each other. A small satellite and a large disk do not enter the conversation with equal leverage. Then comes geometry. A galaxy is not a featureless sphere. A spiral disk has a direction of rotation, a thickness, an orientation, and an internal structure. The orbit of the companion has its own direction as well. The angle between these motions changes how strongly tidal features grow and how effectively gravitational torques act on the gas. Some alignments generate long tails and strong disturbances. Others produce shorter tails or different patterns of inflow. Encounters that pass more directly through one another can compress gas differently from encounters that skim past at greater distance. There is no universal geometry that guarantees the strongest starburst in every galaxy model. Internal structure matters too. A dense central bulge can help stabilize a disk against some of the instabilities that an encounter would otherwise amplify. This is one of the recurring lessons of merger physics. The same external disturbance can produce different internal responses because the galaxies were different before they met. And then there is timing. The first close passage may trigger new star formation, but in many major mergers, the strongest activity appears later, when the galaxies return and their central regions finally approach coalescence. By then, the encounter has already been working on the gas for a long time. Some has moved inward, some has been turned into stars, some has been pushed outward into tails, some has been heated or stirred, some has remained in dense clouds waiting for the next compression. When the two nuclei finally move into the same central region, the gas that survived the earlier stages can be compressed into a much smaller volume. If enough cold material remains, this late phase can produce the most intense star formation of the entire merger, but that last condition is easy to miss. Enough gas has to survive. A merger can begin creating stars before it reaches the stage most favorable to creating even more of them. The first rounds of star formation consume part of the reservoir. Massive stars then return energy and momentum to the surrounding medium. Winds, radiation, and supernova disturb gas that might otherwise have remained available for the final coalescence. The system is therefore spending fuel while it is still arranging the conditions for its largest possible burst. There is a real pair of galaxies where this unfinished balance can be seen in unusual detail. They lie in the constellation Corvus, roughly 60 million light-years from Earth. Their catalogue names are NGC 4038 and NGC 4039, but they are usually called the antennae. The name comes from the long tidal streamers extending far from the central pair. In wide images, those taper outward from the merger, like thin marks drawn across the surrounding sky. Inside the main bodies, the the encounter looks different. The two galactic nuclei are still distinct. Between them lies an overlap region where the disks meet. Molecular gas is abundant there. Dust is thick. Bright young clusters appear across the disturbed material. Infrared observations reveal active star formation that visible light alone cannot fully trace. The antennae are close enough by extragalactic standards that astronomers can study different parts of the merger separately, rather than treating the whole system as one unresolved source. That has made them useful, precisely because they refuse to behave like the simplest picture. Some of the strongest star formation occurs not inside either nucleus, but in the overlap between the disks. This matters. If a merger worked only by driving gas toward the centers, then the brightest star-forming regions should consistently gather around those centers. The antennae show another route. Gas streams meeting between the galaxies can create their own regions of compression, turbulence, and cloud collision. Dense structures can arise away from either nucleus. Massive clusters can form there, while the central regions follow different physical conditions. Even dense gas does not tell the whole story. Measurements across the antennae show that the efficiency with which dense molecular gas forms stars changes from region to region. Some areas with substantial dense gas forms less efficiently than others. The nuclei can contain large dense gas fractions while still showing lower star formation efficiency than parts of the overlap region. So the question becomes more local. Not simply, how much gas does this merger contain? But what state is the gas in here? How fast is it moving? How strongly is it being compressed? How turbulent is it? How long can a dense structure remain intact before feedback or shear disrupts it? At the scale of a whole galaxy, these differences blur together. At the scale of individual regions, they determine whether a cloud becomes a cluster or remains only a cloud. Hubble images of the antennae reveal more than 1,000 bright young star clusters. Some are compact enough and massive enough to survive for a very long time if the merger does not tear them apart. It is possible to look at those clusters and see two errors at once. In the present stage of the system, they are young. Their most massive stars are blue, luminous, and short-lived. They illuminate nearby gas and dust. They mark places where gravitational collapse succeeded during a larger gravitational disturbance. Far in the future, the most durable clusters may look entirely different. Their massive blue stars will be gone. Their surviving populations will be older and redder. The merger itself will no longer be recognizable as two separate spiral galaxies. The long tails may disperse or fall back. The two central structures will have combined into one remnant. A place that now looks crowded with stellar birth may eventually be remembered only through old clusters moving inside a much calmer galaxy. There is a human-scale difficulty in thinking about this, because every stage lasts too long for us to watch the transition directly. An astronomer can spend an entire career studying the antennae and still see the same merger stage. The nuclei will not visibly draw together over a working lifetime. The tidal tails will not change enough to notice by eye. The clusters will age, but not at a rate that turns the system into its future form, while anyone is watching. Knowledge comes instead from comparison. One merger shows an early passage. Another shows a bright overlap region. Another has two nuclei nearly joined. Another has already settled into a single remnant. The universe provides the frames separately, scattered across space, and astronomy tries to understand the sequence. The antennae occupy one of those frames. They demonstrate that a merger can genuinely increase star formation without turning every part of the system into a stellar furnace. They show that star formation can be distributed, selective, and strongly dependent on local conditions. They show that a large gas reservoir can still contain regions where dense material is used inefficiently. Most importantly, they show that the word starburst hides a great deal of internal structure. A galaxy does not burst everywhere at once. It does not convert all available fuel into stars simply because another galaxy has arrived. The encounter changes the possibilities. Gravity rearranges the gas, shocks compress some of it, turbulence reshapes some of it. Feedback begins altering the regions that have already succeeded, and all the while, the clock of the merger keeps moving toward coalescence. The system that reaches that final stage will not carry the same gas it carried into the first passage. By then, part of the fuel has already chosen its future. Some has become stars, some has been scattered, some is still waiting. And whether enough of that waiting gas remains will determine what the merger can become next. A merger cannot make stars from material that is no longer there. That simple limit becomes more important when the story is stretched across cosmic time. The galaxies merging today are not entering their encounters with the same inventories carried by galaxies billions of years ago. The physics of gravity has not changed. Gas still responds to compression. Molecular clouds still collapse when self-gravity overcomes the forces supporting them. But the amount of cold material available to participate in that process has changed enormously. Astronomers often describe mergers with two useful words: wet and dry. A wet merger involves galaxies that still contain significant reservoirs of cold gas. There is material for tidal forces to move, for shocks to compress, for clouds to assemble from, and for central inflows to carry toward the nucleus. When conditions cooperate, the encounter can produce new stars in large numbers. A dry merger is different. The galaxies may contain immense stellar populations. Their dark matter halos may be massive. Their gravitational interaction may be powerful enough to reshape both systems completely. Yet, they enter the encounter with little cold gas, capable of forming stars. The merger still happens. The stars still change orbits. The galaxies can still develop tidal structures. Their central bodies can still move toward one another and eventually combine. What is missing is the raw material for widespread stellar birth. The distinction is not perfectly binary. Real galaxies occupy a continuum. One system may contain a large molecular reservoir, another may contain only a modest amount. A third may technically still possess cold gas while having too little, or gas in the wrong physical state, to support much additional star formation. But the wet and dry language points toward one of the broad changes that has taken place during the history of the universe. Long ago, galaxies were generally richer in gas. Around the era astronomers call cosmic noon, when the universe was only a few billion years old, star formation across the cosmos was far more active than it is today. Galaxies were assembling rapidly. Gas was flowing into halos, feeding disks, forming molecular clouds, and being converted into stars at rates that were common then and unusual now. Many young galaxies were less settled than present-day spirals. Their disks could be thicker and more turbulent. Their gas fractions were often much larger. Their stellar populations were still being built. Place two such galaxies into a major merger, and gravity had an abundant medium to work on. Gas could be driven inward. Dense structures could form throughout disturbed disks. Overlap regions could become sites of rapid collapse. Central concentrations could grow. A merger occurring in that earlier environment did not create the fuel, reorganized fuel, that was already plentiful. That distinction matters because the same gravitational encounter acting on two different eras of the universe can produce very different results. Imagine one pair arriving when both galaxies still carry extensive reservoirs of cold gas. The first passage draws out tails, but also compresses clouds. The disks become unstable. Gas moves inward. New clusters appear. Some of the remaining reservoir survives until the nuclei approach again. producing another opportunity for intense star formation. Now imagine another pair with similar stellar masses and a similar orbit, but arriving many billions of years later. Most of their original cold gas has already passed through previous generations of stars or been moved into phases that are difficult to cool. Their stellar populations are old. Their disks may already be weak or absent. The merger can rearrange hundreds of billions of stars without having enough molecular fuel to build a substantial new generation. From a distance, both encounters can look dramatic. Only one is fertile. The difference began long before either companion appeared. Galaxies spend their histories changing their own future fuel supplies. Every generation of stars locks some matter into long-lived stars and remnants. Massive stars return part of their material through winds and supernova explosions, but that returned gas is often heated and mixed into the interstellar or circumgalactic environment before it can participate in another round of collapse. Gas can also be removed from a galaxy. It can be pushed outward by stellar feedback. It can be heated by energetic activity around a central black hole. It can be stripped in dense environments. And material surrounding the galaxy can become too hot to replenish the disk efficiently. Over billions of years, the balance between consumption, recycling, loss, and replenishment changes. The result can be a galaxy that continues to contain enormous mass while possessing very little material in the particular cold, dense state needed to make new stars. This is common among massive elliptical galaxies in the nearby universe. Their appearance reflects a population dominated by older stars. Many lack the large cold rotating disks associated with continuous star formation in spirals. Their stellar motions are often more disordered, and their structures are supported more by those random motions than by the organized rotation of a thin disk. When two such galaxies merge, the process is dominated by gravity acting on stars and dark matter. There may still be small amounts of gas. There may even be enough material near the center to produce temporary nuclear activity. But a galaxy-wide starburst is no longer an inevitable possibility because the encounter cannot compress a reservoir that does not exist. The growth is then mostly additive. One old stellar population joins another. The remnant becomes more massive. Its stars are redistributed into new orbits. Its outer envelope can expand. Its shape can change. Yet the average age of the stellar population does not suddenly reset because very few new stars are being added. This is one way some of the largest galaxies continue growing after their main era of star formation has already ended. They gain stars without making many stars. There is something useful about seeing galactic evolution in those two separate verbs, to make and to acquire. Early in a galaxy's history, growth can be dominated by making. Gas enters, clouds collapse, new stars appear inside the system. Later, growth can increasingly involve acquisition. Smaller galaxies arrive. Old stellar populations are absorbed. Major dry mergers combine two systems that may both have stopped forming stars long before they met. The galaxy becomes larger while remaining old. And from the point of view of someone observing today, the two phases can be contained inside the same object. The stars near the center may have formed when the universe was far younger. The diffuse outer regions may include material added much later through mergers. One galaxy can therefore hold a record of several different epochs, not as written history, but as distributions of ages, chemical compositions, and stellar motions. Light carries some of that record toward us now. While you are lying beneath an ordinary night sky, telescopes are receiving photons from galaxies, seen when the universe was much more active at making stars. Other photons arrive from nearby massive ellipticals whose dominant stellar populations finished that work long ago. The detector does not receive cosmic history in chronological order. A nearby old galaxy and a distant young one can appear in the same observing night. Astronomers reconstruct the sequence by measuring distance, age spectrum, gas, structure, and motion, then placing those different systems along the long evolution of the universe. From that view, the declining importance of wet mergers is part of a larger transformation. The cosmos has not stopped forming stars. Spiral galaxies still contain molecular clouds. Dwarf galaxies continue turning gas into new stellar populations. Interacting systems still produce bursts when enough fuel and the right physical conditions come together. But the universe is no longer operating at the level of star formation it once did. Its most productive era is behind it. That fact changes the meaning of a merger. At earlier times, two approaching galaxies were more likely to bring abundant star-forming material into the encounter. At later times, especially among massive galaxies, the same kind of gravitational meeting is more likely to be poor in cold gas. The encounter may alter structure far more than it alters the stellar birth rate, and yet gas poverty cannot explain every case. This is where the story becomes more difficult. Astronomers have found merger remnants and post-starburst galaxies that do not fit the simple dry merger picture. Some have already experienced a sharp decline in star formation while still retaining measurable molecular gas. The fuel has not vanished. The galaxy has not simply consumed everything. Cold material remains inside a system that is making far fewer stars than its reservoir might lead us to expect. That observation removes the easiest explanation. If the gas is still present, then something must have changed in the relationship between the gas and gravity. A molecular reservoir can exist without efficiently producing stars because being cold is not enough. Being dense is not always enough. A cloud has to reach a state in which its own gravity can overcome every form of internal support trying to keep it apart. Temperature is one of those forms. Magnetic fields can matter, rotation can matter, and motion inside the gas can matter in a particularly complicated way. The merger that compresses the interstellar medium also stirs it. Gas streams meet, shocks propagate, clouds accelerate, young stars inject energy back into their surroundings. Velocities that were once more orderly become disorganized across a wide range of scales. In one region, that disorder may force material into a dense filament and help gravity begin a collapse. Across a larger region, the same disorder can support gas against collapse by keeping it in constant motion. So a merger can contain the next contradiction inside the first one. It can leave the fuel in place and still make that fuel difficult to use. The galaxies no longer need to be dry. The gas only needs to become resistant to becoming stars. And that resistance begins with turbulence. Turbulence is easy to imagine as motion without pattern. Gas moving in several directions at once. Dense clouds pushed, stretched, broken apart, and compressed again. Currents meeting currents. Energy passing from large scales into smaller ones until the motion becomes complicated enough that no single trajectory tells the whole story. Inside a galaxy merger, that motion can become one of the deciding factors in whether cold gas forms stars or simply remains cold. A molecular cloud does not collapse because it is cold alone. Gravity has to overcome everything that resists collapse. Thermal pressure matters, magnetic fields can matter, rotation matters, and internal motion matters. If the gas is moving rapidly in many directions, those motions provide support. They do not hold a cloud up like a solid structure. Instead, they continually redistribute material, changing densities and velocities before gravity can gather everything into one contracting region. This is sometimes described as turbulent pressure. The phrase is useful as long as we remember that turbulence is not really a pressure in the simple sense of air pressing against the walls of a container. It is a way of representing how disordered matter can oppose gravitational contraction across a region of gas, and mergers generate a great deal of that motion. Tidal forces pull on the disk. Gas streams lose their original circular paths. Material falling inward meets material already orbiting there. Clouds encounter shocks. Young massive stars add winds, radiation, and eventually supernova energy to regions that were already disturbed. The merger is not only squeezing the interstellar medium, it is shaking it. That is why turbulence appears on both sides of the star formation story. At small scales, turbulence can help. Imagine two flows of molecular gas meeting inside an overlap region. Their motion is disordered on the larger scale, but where the flows converge, gas is compressed. A filament can form. A dense knot can appear inside the filament. If enough material gathers there, local gravity can overcome the motions around it. The turbulence has created the density enhancement that allows collapse to begin. This is part of what makes regions like the overlap zone in the antennae so productive. Gas does not need to arrive at the galactic nucleus to be compressed. Local streams can meet far from either center and create star-forming structures where the geometry happens to favor them. Move outward from that single cloud, however, and the same turbulence can have the opposite effect. Across a larger part of the merger, high-velocity dispersion means the gas is moving too vigorously for broad gravitational instabilities to grow efficiently. Structures begin to gather and are disrupted. Density enhancements appear and disperse. Clouds that might have collapsed inside a more settled disk remain dynamically supported. The difference is scale. Local turbulence can make dense pockets. Global turbulence can make those pockets harder to assemble in the first place. That distinction helps explain why a merger can show brilliant star-forming knots while still converting its total molecular reservoir into stars inefficiently. The galaxy is not contradicting itself. Different parts of the gas are living under different conditions at the same time. One region is being compressed, another is being stirred. A third has already formed stars and is now receiving feedback from them. A fourth has been pulled into a tidal feature where its density has fallen. The average star formation rate blends all of those regions together. Inside the merger, the physics remains uneven. This becomes especially important after the most active stage has passed. A post-starburst galaxy can retain spectral evidence that a large population of stars formed recently, and that the rate then fell sharply. The most luminous young stars begin disappearing first because their lives are short. The galaxy's spectrum changes in a way that preserves a temporary record of the burst, even after the burst itself is over. If the decline were caused simply by complete fuel consumption, then very little molecular gas should remain. But observations of many post-starburst systems find that cold molecular gas can still be present. Sometimes, substantial amounts of it remain. The question then becomes difficult to avoid. Why has it not resumed forming stars at the rate expected for that amount of fuel? Part of the answer may be that the merger has not yet finished moving inside the gas. The visible tails can fade. The two stellar nuclei can become one. The broad outline of the remnant can begin to look settled. But turbulence in the interstellar medium does not disappear at the same instant. Energy stored in disordered gas motion takes time to dissipate. Large eddies break into smaller ones. Collisions and shocks gradually convert organized and turbulent motion into heat. Radiation carries some of that energy away. The gas settles only after the disturbance has worked its way down through many scales. That can take tens or hundreds of millions of years across galactic regions. For a human observer, that is almost indistinguishable from permanence. A civilization could arise, change completely, and vanish during a fraction of the time required for a merger remnant's gas to become dynamically ordinary again. Yet, on the timescale of a galaxy, the turbulent period is temporary, and that creates an important limit. If turbulence were the only reason star formation stopped, then the story should eventually reverse. The gas would settle, velocity dispersion would fall, dense clouds would become easier to assemble, star formation would begin again. In some systems, partial recovery may indeed occur, but other merger remnants remain inefficient at forming stars for longer than turbulence alone seems able to explain. This suggests that the disturbance has done more than stir the gas. It may have changed the environment in which that gas has to live. There is also a difference between having molecular gas and having the particular molecular gas most ready to form stars. Astronomers often use carbon monoxide emission to infer the presence of molecular hydrogen, because cold molecular hydrogen itself is difficult to observe directly under the conditions found in most galaxies. Different molecular transitions can reveal different states of the gas, helping distinguish broadly distributed cooler material from denser and more strongly excited regions. A galaxy can therefore possess a large molecular reservoir while having only a small fraction of that reservoir in the dense structures most closely associated with immediate star formation. That distinction is critical. The fuel is present in a broad accounting sense, but much of it has not reached the final physical state needed for collapse. It is like having an enormous watershed without having much water gathered into the narrow channels that can actually turn a turbine. The total amount matters, but its organization matters just as much. After a merger, molecular gas can remain spread through the remnant in a diffuse, dynamically disturbed state. It is cold enough to remain molecular. It is massive enough to be detected. Yet the route from diffuse molecular material to dense cloud core has become inefficient. Turbulence contributes to that inefficiency. The changing gravitational structure of the remnant may contribute as well. And another source of energy is beginning to enter the story from the center. During the merger, not all inward-moving gas ends its journey in star-forming clouds. Some loses enough angular momentum to travel much farther. From kiloparsec scales, it moves into the central hundreds of parsecs. From there, a smaller fraction continues inward again. The amount becomes smaller as the distance shrinks, but the consequences grow. At the center of a massive galaxy sits a supermassive black hole. Most of the time, that black hole can remain comparatively inactive because very little material reaches the region where it can be accreted. The galaxy may contain enormous amounts of gas farther out, but angular momentum keeps most of that gas in orbit. A merger changes that arrangement. The same asymmetries that drive gas toward dense star-forming regions can also deliver material toward the nucleus. Bars, distorted orbits, gravitational torques, and repeated passages remove angular momentum step by step. The black hole does not pull gas across the entire galaxy like a drain. The galaxy has to hand the material inward. By the time some of it reaches the central region, the merger has already completed much of that work. Then accretion begins to increase. Gas falling toward the black hole heats as it moves through the compact region around it. Radiation rises. Winds can develop. In some states, narrow jets carry energy far beyond the immediate nucleus. The black hole itself remains dark. The environment around it does not. And now the merger has created another feedback loop. Gas helped awaken the central black hole. The awakened nucleus can begin changing what happens to the remaining gas. This does not mean every merging galaxy becomes dominated by an active galactic nucleus, or that black hole activity always shuts star formation down. Many active nuclei exist without major mergers, and many mergers never produce a luminous phase strong enough to control the whole galaxy. But when the conditions align, the central black hole becomes one more reason. The star-forming future of the remnant can diverge from the simple expectation that compressed gas must keep making stars. Turbulence can delay collapse, while the gas is still there. The nucleus can then begin changing, whether that gas will remain available at all. By the time gas reaches the innermost region of a merging galaxy, the distances involved have changed almost beyond recognition. The merger began across hundreds of thousands of light years. Tidal forces worked across entire stellar disks. Streams of gas moved through regions measured in kiloparsecs. Now a small fraction of that material has traveled inward far enough that the central black hole begins to matter directly. The amount arriving there may be tiny compared with the galaxy as a whole. Its influence does not have to be. Gas approaching a supermassive black hole cannot simply fall straight through the horizon. It carries angular momentum, so it tends to gather into a rotating accretion flow. Friction, magnetic fields, and turbulence allow material within that flow to move gradually inward. In the process, gravitational energy is converted into radiation and motion. A black hole that had been faint can become an active galactic nucleus. The nucleus may brighten across wavelengths, ranging from radio to X-rays. Winds may emerge from the accretion region. In some systems, narrow jets extend outward, far beyond the scale of the central engine that launched them. It is tempting to imagine this as the moment the black hole switches star formation off. The evidence does not support anything quite that simple. Active galactic nuclei are found in galaxies that are still forming stars. Many galaxies stop forming stars without showing evidence that a major merger has recently occurred. And studies of post-merger systems indicate that black hole feedback is unlikely to be the only mechanism responsible for rapid quenching in every case. Some observations instead point toward gas consumption, stellar feedback, and changes throughout the disk as important parts of the transition. The black hole is therefore better understood as one participant in a system that has already been transformed. What makes it important is reach. Radiation produced near the center can ionize and heat surrounding material. Winds can carry momentum into the interstellar medium. Jets can interact with gas much farther away. The energy begins in a region smaller than the galaxy by many orders of magnitude, yet under favorable conditions, its consequences can propagate through a substantial part of the host. The first effect is local. Gas near an active nucleus can be heated until its pressure rises, and its ability to remain in cold star forming structures is reduced. Dense material can be disrupted. Clouds can be accelerated. Some gas may be pushed away from the center before it has time to collapse. But heating has a limitation. Gas can cool. Atoms and ions collide. Energy is radiated away. A parcel that becomes hot does not necessarily remain hot forever if it stays gravitationally bound, and if nothing continues supplying energy, it may cool again, settle again, and eventually return to conditions where stars can form. So temporarily warming the fuel is not the same as permanently removing the galaxy's ability to make stars. Outflows introduce another possibility. Instead of merely changing the temperature of gas, an active nucleus can give gas momentum. Material begins to move outward. Some of it may travel only a short distance before slowing and returning. This creates a galactic fountain, with gas leaving the central region and later falling back. Some may reach the outer galaxy. Under stronger conditions, part of the flow can enter the halo or escape the galaxy's central gravitational potential altogether. Observations of rapidly quenched galaxies show that multi-phase outflows can remove star-forming material. Although even powerful outflows do not necessarily eject every gas phase from the halo permanently. That difference between displacement and permanent loss matters over long timescales. A galaxy does not depend only on the gas sitting inside its visible disk at one particular moment. It also lives inside a much larger reservoir. Beyond the stars lies the circumgalactic medium, an extended atmosphere of diffuse gas associated with the galaxy's dark matter halo. Some of this material is hot, some occupies cooler phases, some is enriched with elements produced by earlier generations of stars and carried outward by winds. Under the right conditions, halo gas can cool and eventually replenish the galaxy. A molecular cloud that forms a star today does not have to be replaced by gas that was already sitting beside it yesterday. The larger galactic ecosystem can supply new material over time. That means a galaxy can survive the loss of some cold gas from its disk if the surrounding reservoir continues feeding it. For star formation to remain suppressed for billions of years, changing that supply can matter as much as removing the fuel that is already present. This is where black hole feedback becomes less like a single outburst and more like long-term maintenance. Mechanical energy reaching the halo can keep part of the circumgalactic medium hot and diffuse. Cooling becomes less efficient. Material that might otherwise condense and return to the galaxy remains suspended at large radii. The disk continues using whatever cold gas is left. The replacement arrives more slowly. The reservoir inside the galaxy declines, not necessarily because one event removed all of it, but because consumption continues while replenishment weakens. In the Illustris family of cosmological simulations, low accretion black hole feedback plays an important role in maintaining massive galaxies in a quenched state. The model affects both gas within galaxies and the surrounding circumgalactic medium, producing a combination of ejective and preventive effects. That is a model, not a direct photograph of the process. The distinction is important. Cosmological simulations cannot resolve every molecular cloud, every shock front, every magnetic structure, and every interaction between an outflow and a clumpy interstellar medium. Across the full history of thousands of galaxies, processes below the available resolution have to be represented through physical prescriptions. Change those prescriptions and the details of quenching can change. Observations present their own challenge. A galaxy may show evidence of an outflow and declining star formation at the same time. Yet, coincidence in time does not automatically prove that the outflow caused the decline. The merger itself may have consumed part of the gas. Turbulence may already have lowered star formation efficiency. The structure of the remnant may be changing. The halo may have been hot before the galaxies met. A black hole can contribute without being the original cause. It can also help prevent recovery after some other process caused the first decline. This may be one of the more useful ways to think about feedback. Not always as the hand that stops star formation into single movement, but sometimes as the process that makes restarting increasingly difficult. There are observations that fit this more complicated picture. Post-starburst galaxies can retain compact, disturbed molecular reservoirs while forming stars. Inefficient suggests that gas removal alone cannot explain their state. Active nuclei are present in some of these systems, but not all, leaving room for several mechanisms to act together. The merger has already changed the gas before the black hole becomes important. The gas has been compressed and stirred. Some has formed stars. Some has traveled inward. Some has moved outward. The central black hole receives a small portion of that rearranged material and returns energy to a system that is already far from equilibrium. What follows depends on where that energy goes. If it couples weakly to the surrounding medium, the nucleus may brighten and later fade without changing the galaxy's long-term future very much. If it heats dense gas that later cools again, star formation may only pause. If it accelerates cold material outward, part of the immediate fuel supply can be lost. And if energy continues reaching the extended halo, the galaxy may find that the larger reservoir from which recovery once seemed possible is no longer cooling efficiently enough to help. No single boundary marks the transition. There is only a gradual separation between having matter and having matter available in the right state, at the right density, at the right temperature, with the right motions, at the right place. The galaxy can remain surrounded by gas and still become starved. It can retain molecular material and still form very few stars. It can contain a supermassive black hole that has grown brighter while the stellar population around it begins aging toward a less active future. And after the nucleus fades, another consequence of the merger remains. The stars themselves have been rearranged. The old disks that once provided an ordered gravitational setting for the gas may no longer exist in their original form. The merger has changed not only the fuel and the forces acting upon it, it has changed the shape of the place where future stars would have to form. After the two galaxies have become one, the merger leaves behind more than disturbed gas and an altered halo. It leaves a new gravitational structure. Before the encounter, much of the stellar mass may have belonged to rotating disks. Stars traveled along broadly organized paths around their galactic centers. The gas lived inside much of the same flattened geometry, and with its environment, small variations in density could sometimes grow into larger ones. The merger, it disrupts that arrangement. Repeated gravitational encounters scatter stellar orbits. Some angular momentum is transferred into tidal material. Some is redistributed between different components of the galaxies. By the time the central regions have coalesced, a system that began with two recognizable disks can emerge with a much larger spheroidal component, supported less by ordered rotation and more by stars moving along many different kinds of orbits. That transformation changes the appearance of the galaxy. It may also change what the remaining gas is able to do. In 2009, Marie Martig and colleagues explored a mechanism that became known as morphological quenching. Their simulations showed that building a massive stellar spheroid could stabilize a gas disk against gravitational fragmentation, even while gas remained present and additional material continued to arrive. The idea begins with instability. Star formation requires gas to gather. A small overdensity has to survive long enough for gravity to amplify it. Material is drawn inward. The region becomes denser. Its gravity becomes stronger, drawing in more material. If nothing prevents this growth, a large cloud can eventually fragment into smaller, dense regions and begin forming stars. But a disk is not governed by gravity alone. Its rotation resists some forms of collapse. Gas pressure and turbulent motion resist others. Astronomers describe part of this balance using quantities related to the tumor stability parameter. The details depend on whether gas, stars, or both components are being considered, but the physical question is straightforward. Will a disturbance grow, or will the structure of the disk erase it before gravity can take control? During the morphological quenching phase in the original simulations, the stellar spheroid altered that balance enough that much of the gas disk became stable against the formation of bound star, forming clumps. The gas had not been completely expelled. Its supply had not necessarily ended. The gravitational setting had changed. This gives the merger a consequence very different from the ones we have followed so far. Turbulence acts through motion. Black hole feedback acts through energy and momentum. Morphological stabilization acts through structure. Nothing has to strike the gas. Nothing has to heat every cloud. Nothing has to push the entire reservoir beyond the galaxy. The stars themselves, simply by occupying a different distribution after the merger, can help make large-scale fragmentation more difficult. The remnant has inherited a geometry that does not encourage the remaining gas to organize itself as readily as it once did. It is important not to make this mechanism larger than the evidence allows. Morphological quenching is not a universal explanation for every passive galaxy, nor does it guarantee permanent shutdown on its own. Later observational and theoretical work has continued to examine how strongly bulges and spheroids suppress instability under different gas fractions and dynamical conditions. Real galaxies contain too many interacting processes for shape alone to explain everything, but shape does not have to explain everything to matter. Consider a merger remnant that has already passed through several earlier changes. Its gas reservoir has been reduced but not erased. Its molecular medium is turbulent. The fraction assembled into dense star-forming structures is lower than before. Its central black hole has injected energy into parts of the interstellar medium and halo, then place what remains inside a stellar potential that is more resistant to disk fragmentation. Each mechanism may be incomplete by itself. Together, they begin to reinforce one another. A cloud that survives the turbulence still has to become gravitationally unstable. Gas that remains gravitationally unstable still has to avoid disruption. Material that could eventually settle must still be supplied from outside, and that last requirement takes us beyond the visible body of the galaxy. The circumgalactic medium extends far outside the stellar system, filling a large fraction of the dark matter halo with diffuse gas spread across many temperatures and densities. It is not empty space surrounding the galaxy. It is part of the galaxy's long-term material cycle. Gas consumed by star formation does not have to represent a permanent loss if new material can cool from the halo and enter the disk. Matter expelled by stellar winds may travel outward, mix with halo gas, cool again, and later return. Material arriving from the larger cosmic environment can also enter this cycle. A galaxy, therefore, depends not only on what it possesses now, but on what it can receive later. Merger simulations that include the circumgalactic environment have made this especially clear. Work following gas through major encounters has found that material originating in the CGM can contribute significantly to star formation near coalescence and can also help fuel later renewed star formation in the remnant. The merger is not a closed container. While gas is being consumed inside the disks, additional gas can be arriving from outside them. That changes what permanent quenching requires. Using up the disk reservoir is not enough if the halo simply replaces it. Moving gas outward is not enough if that material later cools and falls back. Temporarily heating the inner galaxy is not enough if fresh fuel continues arriving from larger radii. A lasting decline requires the entire cycle to become less favorable to replenishment. This is where the processes from the previous chapter connect with the new structure of the remnant. AGN-driven energy can reach into the halo and lengthen cooling times. A massive halo itself can maintain gas at temperatures where cooling becomes inefficient. The disk inside may be increasingly stabilized by its spheroidal stellar environment, and the gas already present may remain turbulent or poorly concentrated into dense clouds. The galaxy can therefore be restricted at several different stages of the same supply chain. Far outside, gas has difficulty cooling. Closer in, less material reaches the disk. Inside the disk, diffuse molecular gas has difficulty assembling into unstable clouds. Within those clouds, turbulence and feedback can interrupt collapse. At the final step, only a fraction reaches the densities where stars actually form. No single barrier needs to be absolute. Star formation only has to become inefficient at enough of them. This helps explain one of the stranger states a merger remnant can occupy. It can possess gas without behaving like a gas-rich star-forming galaxy. The halo may still contain enormous quantities of matter. The inner galaxy may still show molecular emission. Nothing about the system needs to be physically empty. What has disappeared is the easy path from reservoir to star. The distinction is subtle when we reduce galaxies to images. A photograph shows where the stars already are, it does not immediately reveal the stability of a gas disk, the cooling time of the halo, the velocity field inside molecular clouds, or the fraction of gas dense enough to collapse. Two galaxies can therefore contain comparable amounts of matter and have radically different futures. One continually organizes part of its gas into new stars. The other holds much of its material in states from which that organization is difficult. Over time, the difference becomes visible in the stellar population. Massive blue stars die first. Without replacements, the ultraviolet weakens. The brightest signatures of young stellar populations fade. Longer-lived, lower-mass stars increasingly dominate what remains. The galaxy becomes redder, not because its old stars suddenly changed, but because fewer young ones are arriving to alter mixture. The transformation can continue long after the great tidal structures that once announced the merger have faded. A distant observer encountering the remnant much later might see a smooth, massive galaxy with an aging stellar population and find little immediate evidence of the complicated sequence that produced it. The gas once compressed into new clusters, the turbulence that later resisted collapse, the black hole that received part of the inflow, the halo that became harder to cool, the stellar disks that were reorganized into a spheroid. All of these can become difficult to reconstruct from the final appearance alone. And this brings the question of causation into sharper focus. If the remnant eventually stops forming stars, which part of this sequence deserves the credit? The merger, the black hole, the halo, the loss of cold gas, the turbulence, the new morphology, or conditions that existed before the galaxies ever began falling toward one another? By the time two galaxies meet, neither arrives as an untouched system. Each brings a history of star formation, gas consumption, black hole growth, previous interactions, and halo evolution. The merger changes that history, but it does not begin it. And in the final stage of this journey, that distinction becomes the most important one. By the time a merger reaches its final form, the easiest explanations have usually failed. If the galaxy has stopped forming stars, it may be tempting to point to the merger and call it the cause. Two systems met, their structure was disturbed. Their gas was compressed, scattered, heated, and driven inward. The central black hole may have brightened. The stellar disks may have been transformed. The halo may have become harder to cool. All of that can be true. And still, the merger may not have begun the decline from nothing. Galaxies arrive at an encounter carrying long histories inside them. A massive galaxy may already have a large central black hole before the first tidal tail appears. Its cold gas fraction may already be falling. Its halo may already be hot enough that fresh material cools only slowly. Its disk may already be less capable of sustaining the kind of instability that builds new molecular clouds. The merger then acts on a system that was never neutral. This is one reason causation becomes difficult to assign. Suppose a gas-rich galaxy with a modest black hole enters a major merger, while its halo is still able to supply fresh material. The encounter can trigger new star formation. Some gas is consumed, some is expelled, and some is stirred. But after the disturbance fades, cooling from the surrounding halo may continue. The disk can rebuild part of its reservoir. Star formation may recover. Now imagine another galaxy entering a similar encounter much later in its own evolution. Its cold gas is already limited. Its central black hole is more massive. Its halo has a long cooling time. The merger drives the remaining gas inward, produces a brief final period of star formation, feeds the nucleus, increases turbulence, and rearranges the stellar structure. Nothing in that sequence needs to be overwhelmingly strong by itself. Together, the processes can push the galaxy across a threshold from which recovery becomes difficult. This is perhaps the most useful way to understand why mergers sometimes appear to shut star formation down. They can be catalysts. They can gather several mechanisms into the same interval of cosmic time. Gas consumption accelerates. Turbulence rises. Black hole activity may increase. The stellar structure changes. The route by which the halo replenishes the disk can weaken. A transition that might otherwise have taken much longer can become compressed into a relatively short phase. The merger does not have to invent the conditions for quenching. It can bring them together. That interpretation also explains why no single merger outcome should be treated as universal. Two galaxies can have similar masses and still carry different gas fractions. They can have similar gas fractions and different black hole masses. They can have similar black holes and very different halos. They can enter with different disk structures, different orbital histories, different environments, and different amounts of material already committed to previous generations of stars. The gravitational encounter follows the same physical laws in every case. The initial conditions do not repeat. This is why one merger becomes a brilliant starburst, another produces only modest enhancement, and another ends with a galaxy that rapidly becomes passive. The word merger describes the meeting. It does not describe the outcome. That outcome is written by the state of the galaxies before they touch, and by the chain of processes that follows. After gravity begins to rearrange them, there is also a deeper limit to what astronomers can know from any single remnant. We observe galaxies at particular moments. A spectrum can reveal that star formation declined recently. Molecular emission can show that gas remains. X-rays or radio emission can reveal an active nucleus. Imaging can preserve tidal features that identify a past interaction. But the complete history is not present in one measurement. The galaxy before the merger is gone. Its exact gas distribution before first passage cannot be recovered perfectly. The previous state of its halo is reconstructed indirectly. The activity history of its black hole is inferred from traces that may fade on very different timescales from the stars. So the question of whether a merger caused quenching sometimes has no clean yes or no answer. The more accurate question is what role the merger played in a transition that already had several possible causes. In some galaxies, it may be decisive. In others, it may accelerate a decline that had already begun. In still others, the merger may trigger a burst and fail to quench the remnant at all. That uncertainty is not a weakness in the science. It is what becomes visible when the system is studied closely enough to stop forcing one mechanism onto every galaxy. The final remnant may look simple from far away. A smooth body of old stars, little blue light, no obvious spiral arms. Perhaps faint tidal debris at the edge, slowly dispersing into the halo. But hidden inside that calm appearance is a history of competing processes. Gravity first brought the galaxies together. The encounter compressed some gas and made new stars. The same disturbance stirred other gas into less efficient states. Inflow carried material toward the center. Feedback changed the inner galaxy and perhaps the halo. The stellar structure became more stable against fragmentation, and the supply of future fuel may have weakened until the remaining reservoir was no longer enough to sustain what came before. Nothing had to happen in a single instant. A galaxy can stop forming stars the way it formed in the first place, through many physical processes acting across different scales. Clouds, disks, black holes, halos. Billions of stars moving through a changing gravitational field. By the time the merger is over, even the idea of an ending becomes difficult to place. The tidal tails may continue orbiting for ages. Some expelled gas may return. A small of star formation may persist in isolated pockets. The central black hole may brighten again long after the main burst has faded. The remnant continues evolving because galaxies never become truly finished objects. They only enter new regimes, and one of those regimes is a long period in which the making of new stars becomes rare. The most striking part is that the merger can produce both sides of that transition. It can create the compression that helps stars form. It can also help establish the conditions that prevent later clouds from collapsing. The same encounter can briefly increase the rate of stellar birth and still leave behind a system where future birth is difficult. There is no contradiction once the timescales are allowed to separate. What favors collapse now can help remove, heat, stabilize, or isolate the fuel later. A merger is not one physical effect. It is a sequence, and a galaxy is not merely the place where that sequence happens. It carries the memory of every stage forward in its gas, its stars, its black hole, and the halo surrounding them. Long after the two original galaxies have lost their separate names, that memory remains in the structure of the remnant. The last tidal arc fades into the halo,